Solve the system of nonlinear equations. Then graph the equations in the system. So to get us started, let's simply begin by identifying the equations in this system. And looking at equation number 1, we see that we are working with a circle centered at the ordered pair 5, 0 with a radius of 5. And looking at equation 2, here we have a square root. Now, to solve this system of nonlinear equations algebraically, we're going to begin by substituting equation 2 into equation 1. So in other words, we are going to replace the y in the circle with the square root equation, 3 times the square root of x minus 8. So now that we have the equation in terms of the single variable x, we are ready to start solving. Now, in order for us to solve, we need to simplify using the properties of exponents. So we can expand the first binomial product out to x minus 5 times x minus 5. And then using the properties of exponents on the square root, we can rewrite this as 3 squared times the square root of x minus 8 squared is all equal to 25. Now, applying the FOIL method on the first binomial product, we are left with x squared minus 10x plus 25. And this will now be plus 3 squared leaves us with 9. And if we square the square root, this is x minus 8. The square and the square root cancel each other out. Now, distributing the 9 through to both terms, and then combining up those like terms, we are left on the left-hand side with x squared minus x minus 47 is equal to 25. And of course, we recall that in order to solve a quadratic equation, we need to bring all the terms to one side. So subtracting 25 from both sides of the equation, we are left with the quadratic equation, x squared minus x minus 72 is equal to 0, which we can now factor to the binomial product, x minus 9 multiplied by x plus 8 is equal to 0. And applying the 0 factor property, we can now solve each one of these binomials separately to find the x-coordinates of our intersection points. So in case number 1, if we add 9 to both sides of this equation, we're left with the x-coordinate, x equals 9. And very similarly, in case number 2, if we subtract 8 from both sides, we are left with x equals negative 8. Now, for each of these x values, we want to go ahead and find the corresponding y value by substituting x into either equation. So I'm going to go ahead and use the square root equation, y is equal to 3 times the square root of x minus 8, but feel free to use the equation of the circle as well. Now, in case 1, when x is equal to 9, when we substitute this into the square root, we are left with y is equal to 3. So our first intersection point is the ordered pair 9, 3. And very similarly, when x is equal to negative 8, when we substitute this into the square root equation, something interesting happens. Notice that when we simplify, we realize that we end up with y is equal to 3 times the square root of negative 16, which is not a real number. We know the square root of a negative is an imaginary number. So this means that we are going to exclude x equals negative 8 because this is not a real solution. So in this case, these two equations are only going to intersect at the single point 9, 3. So now that we have this intersection point, let's go ahead and consider what the graph of the system of equations looks like. So we are now ready to graph the equations in the given system. And to get us started, we begin by recalling that these two equations intersect at a single ordered pair, 9, 3. And as always, to make sure that the sketches of our graphs are as accurate as possible, let's begin by finding the intercepts for each equation. So starting with the equation of the circle, centered at the ordered pair 5, 0, with a radius of 5, we can use the center point and our radial length to find the intercepts. So starting at the point 5, 0, and moving 5 units to the left and 5 units to the right, we can see that we have two x-intercepts, one at the ordered pair 0, 0, and another at the ordered pair 10, 0. Now we can also see that one of the x-intercepts at the origin is also the y-intercept for the circle. Now, to make sure that we can visualize the graph of the circle, let's start at the center point again and move 5 units up to the ordered pair 5, 5. And again, starting at the center point 5, 0 and moving 5 units down to the ordered pair 5, negative 5. Now we have 4 points on the circumference of the circle, and we can connect these ordered pairs with a smooth curve to see the graph of the circle. Now we want to do the same thing for the equation of the square root. So for the x-intercept, we're going to let y equals 0 and solve for x, which produces x equals 8. So we have an x-intercept at the ordered pair 8, 0. And for the y-intercept, we know that we're going to let x equal 0 and solve for y. However, notice when we solve for y that we end up with 3 times the square root of negative 8, which is not a real number. So this is letting us know that the graph of the square root does not have a y-intercept. However, we have enough information to sketch a graph of the square root. We can use our x-intercept and the point of intersection 9, 3 and connect these two ordered pairs with a smooth curve to see the graph of the square root. And there you have it. Here is the graph of the equations in our system.